Last time we made some progress in getting to an understanding of chemical kinetics, and let's review that a little bit because this stuff was very basic, very important for everything that comes next. What's going to come next is we're going to begin exploring how kinetics behaves in certain simple and very illustrative cases, but this basic stuff is really important, so let's go over it a little bit. First of all, we talked about the fact that a rate of reaction is a time derivative of some kind of concentration. And I commented that the concentration can be any of the reactants or products or any of the intermediates even. And it can also be things that are related to that. But if you're in a situation where there are no intermediates, so it's an elementary reaction, or if all the intermediate concentrations are at steady state, so they're not changing with time, then the stoichiometry of the reaction requires a relationship between all of the time derivatives for all of the species that are involved in the reaction, both reactants and products, and we will use that set of relationships fairly extensively in what's to come, so we won't forget about it. I emphasized last time that this isn't always true. If you've got intermediates and they're building up or decaying away, then this isn't true anymore. But it's almost always true, and so it's a good thing to, and in the cases we're going to be talking about, it'll be mostly elementary reactions, and so it's always true in those cases. So it's a good set of relationships to keep in mind. Then we talked about the fact that when we write down an overall reaction like this water-forming reaction, it's really not the whole story. It's an overall reaction that's keeping track of the stoichiometry, but it's not telling us what's going on microscopically. In order to know what's going on microscopically, you have to write a mechanism, and the mechanism is composed of elementary reactions. And the distinction between an overall reaction like this one and elementary reactions like this one, like all these, is that the elementary reactions show everything that's involved in the reaction, whereas an overall reaction like this has hidden stuff. It has intermediates, which are species that don't show up in the overall reaction. And so if we look at each of these, this is the mechanism, or this is a proposed mechanism. It's not really the correct one, but a possible mechanism for this overall reaction. Then you can see that these species, the ones circled in blue here, don't show up in the overall reaction. And that's what makes them intermediates, and that's what makes this guy an overall reaction and not an elementary reaction. But on the other hand, if you look at each of these smaller reactions that go into the mechanism, then everything that happens in those reactions is written out, and there aren't any hidden intermediates, and so these are elementary reactions. Mechanisms are always composed only of elementary reactions. There's much to say about elementary reactions. We'll use them widely in what's coming next. And most of what we're going to talk about, in fact, is about elementary reactions, not about the overall reactions, as you can see. And let me say that the project for most research investigations into the kinetics of overall reactions like this, the purpose of those investigations is usually to try to find out what these mechanisms are. Once you've got the mechanism, you can analyze the kinetics of any reaction. So finding the mechanism is oftentimes the goal, usually the goal. We talked about the fact that if I have a reaction, either an overall reaction or an elementary reaction, then there is a relationship between the rate of reaction and the concentrations of the products and reactants that are part of that reaction. And it's usually a power law like this one. So in this case, the rate of reaction is equal to a rate constant. That little k gets a lot of attention later. It's the thing that contains all the information about the nature of the reactants and products. And so it'll get a lot of attention later. And then it depends on the powers, usually on just the reactant concentrations, though sometimes, occasionally, also the product concentrations, to powers, and those powers are called orders. So the power that the A concentration is raised to is the order for A. The power for B is the order for B. And then there's an overall order as well, which is just the sum of all the powers. For an overall reaction, you can't tell what the rate law will be just by looking at the reaction. But for elementary reactions, you can. And so, as I said, elementary reactions are very special and useful in a lot of ways. This is one of the ways. You can tell what the rate law is going to be for an elementary reaction. So, for a molecularity 1 unimolecular reaction, just one reactant, and that reactant changes on its own somehow, then the rate law is K times A to the first power. There's a 1 here, there's a 1 here, and the stoichiometric coefficients correspond to the powers or orders for elementary reactions, but not for overall reactions. For a second order, a set of either of these two second order reactions, if you've got two of the same molecules colliding with each other, then the rate law is to the second power. If I've got two different molecules colliding with each other, then overall it's second order, but each one appears only with a 1, with a stoichiometric coefficient of 1, so each one only appears to the first order. And we talked about the general case before, but the general case really rarely shows up, so I won't talk about that here. All right, that's pretty much where we are. We're now ready to go on, and I think I'm going to leave this page up here because I think the resolution is high enough for people to be able to see the other page anyway, and it's useful to have that second page over there, so we'll leave it up and hope that works. Let's now talk about special cases where, I think we were further along here. Let me see. Yes, down here is where we were. Where we consider the time behavior for simple reactions, especially elementary reactions like this one here. So A goes to products. I've said earlier, and it's true, that the rate of reaction is equal to, or is proportional to anyway, well, let's just say equal to in this case, minus the A concentration with respect to T, and it's also equal to the P concentration with respect to T. But just up above, I said that that's also equal to K times the A concentration. If I combine these two, then I get what's called a rate equation. This is a rate law. This whole thing is a rate equation. Or at least that's my nomenclature for these things. So there's a difference between a rate law and a rate equation in my nomenclature, and I'll use that nomenclature throughout. But this rate equation is a differential equation. It's something that can be solved, and if we solve it, then we can get the time behavior. We can get how the concentration of A changes with time. And we can do that in this case especially nicely because it's the simplest possible case. It's a first-order rate equation, as it says over here. So let's do that. Let's solve this differential equation. And now we'll use this page over here. If I have my differential equation, dA dt is equal to minus K times A, then I can rearrange dA over A is equal to minus K times dt, and now I can integrate both sides. The integral dA over A, from, let me emphasize that, the limits here on the integration, from the value of A when we're at time 0 to the value of A at some later time, that has to equal the integral from t equals 0 up to t of minus K dt. And now doing both of those integrals, we get that the log of A from A0 to A is equal to minus kt, and substituting in these limits, we get that the log of A minus the log of A0, the initial concentration, is equal to minus kt, or log of A over A0 is equal to minus kt. And now taking the antilog, or the exponential of both sides, we get A over A0 is equal to e to the minus kt. And that just means A is equal to A0 e to the minus kt. All right, I went through that. I think a lot of you probably didn't need to go through that in detail, but just to make sure everybody's on the same page. That's one simple example of solving a rate equation, a differential equation, in order to get A, the concentration, as a function of time. Now let's look at what that means. And for that, we don't need that page so much. So here's our integrated rate equation. And that's what I'll call expressions like this, no matter how complicated they get. I'll call them integrated rate equations. You can call them concentration expressions or something like that. I think your book has a different name for it. There is no real standard name, so I'll just call them integrated rate equations. This is the rate equation itself, and this is an integrated rate equation because it's been integrated. Let's just look again to see what the parameters are that go into this equation. This is the initial concentration. That's how much A we had to start with. That's the rate constant, same as this guy up here. And of course, T is time. And this gives A as a function of time. We normally won't write this little parentheses T there that indicates that this is a function of time, because that's normally just understood. And it gets a little tedious to write it out every time. All right. We also have, and this is useful at this point, that these two rates are related to each other, right? That's the generalized, let me go up here, that's the example in this case of this set of relationships, right? Oh, come on, there we go. So this set of relationships for this particular simple case just becomes this set of relationships here. And we can integrate both sides of this. And if we do, we'll get P over here, we'll get A over here, and that means that the concentration of A plus the concentration of product has to be equal to a constant. That makes sense, right? If we go up and look at our overall reaction here, our elementary reaction really, what this is saying is that every time we lose an A, we gain a P. And that means that if I add the A's and the P's together, things can never change, right? Every time I change A, I'm changing P by the same amount in the opposite direction, so the sum always adds up to a constant. Furthermore, if I say, for the sake of exploring the most interesting case, that the concentration of P is equal to 0 when T is equal to 0, that is, P sub 0 is equal to 0. Then, at time equals 0, this P is equal to 0, and this A is equal to A0, which means that the constant is just equal to A0. And so we can say that A plus P, where do I have it here? Well, I didn't write it there, but A plus P has to equal to the initial concentration of A at all times. These are functions of time, after all. And so this relationship must hold. It follows from this relationship, must hold at all times. And that means that if this is A, that's the expression for A as a function of time, then we've also got the expression for P as a function of time. And there it is. If we plot both of those out now, you get curves that look like this. So the A concentration is decreasing, of course. Let's look at our reaction A goes to P. This is an irreversible reaction, right? The A can go to P, but it can never go back, which means that A always has to go away. And by the time we're done, if we wait long enough, all the A has to go away. It's an irreversible reaction. It must go to completion, and that means the curve must continually go down, and eventually, at long enough time, it'll go to 0. Likewise, once P is formed, it can never disappear. The P always has to build up, and that's what this curve is showing. And this constant line here that I pointed out in the notes is just showing that the sum of these two curves at every point, the P curve plus the A curve, always adds up to this constant value. That's what this relationship is saying. All right. That's an exponentially decaying, this A curve, this one, is an exponentially decaying curve. That's what this relationship is saying up above. The A concentration is decaying exponentially with time. But just looking at it with normal human eyes, you can't really tell whether that's an exponential decay or some other kind of decaying curve. You can tell, of course, that it's going down, but you can't tell how it's going down exactly. So how do we tell if we're getting an exponential first-order behavior or possibly getting second-order behavior or some other complicated thing? Well, there is a way. In the course of our derivation over here on the right-hand side, at one point during the course of the derivation, we had this relationship, right? The logarithm of A minus the logarithm of A at time 0 is equal to minus kt. And that means that we have this relationship. The logarithm of A is equal to a constant, just the log of the initial concentration, minus kt. If we call this quantity y and this quantity b, and if we think of t as x, then we have y equals mx plus b. That's the equation for a straight line, which means that if we plot the logarithm of A versus time, we should get a straight line, and the slope of that straight line should equal minus k. And the intercept on the y-axis of that straight line should equal the log of A0. That's only true, though, if this was a first-order reaction to begin with, if we had exponentially decaying behavior in the first place. You only get a true straight line when you plot log of A versus t for a first-order reaction. And that means that this kind of plot, log A versus t, is a diagnostic plot for first-order behavior. If you want to know whether, if you make some experimental measurements or you're given some data in a homework problem, let's say, and that behavior gives rise to a plot or a behavior that's decaying like this, and you want to know if it's really first order or not, well, there's other tests, easier tests than this one, but one way of answering that question is to make a plot of log A versus t and see if it gives you a straight line. If it curves a little bit, then it's not exponential behavior, it's not a first order reaction. Only if it's dead straight is it a first-order reaction. Now, in real circumstances, you don't have perfect mathematical data. You've got experimental noise, and so you can't always tell if it's perfectly straight line or not. But it's a good test. If you get something that looks like a straight line, then you know it's at least close to exponential first-order behavior. A whole lot of processes, even things that are nominally very complicated, obey first-order laws. So this kind of situation where it looks at least first order is very common. All right, there's another useful concept that goes pretty much mainly or only with first-order behavior. Let's suppose we ask, how long does it take for the initial concentration of A to decay to half of its original value? So here's A0. Here's a half A0. How long does it take, and here's the time it took here, how long does it take to get to that point where you've lost half of your initial concentration? That's the half-life. And we can solve for what that half-life is using our integrated rate law. If I set the concentration equal to half of the initial concentration, then I get that 1/2 is equal to e to the minus kt 1/2. Taking the logarithm of both sides and solving gives me that the half-life is equal to the natural logarithm of 2 divided by the rate constant. Lots of implications follow from that relationship. It is oftentimes convenient to actually evaluate this logarithm of 2. It's about 0.693, at least to 3 decimal places, that's correct. And so 0.693 over k is a good approximation anyway for the half-life of a first-order reaction. Now, This nice relationship only works for first-order reactions. It only works for exponentially decaying behavior and therefore only for first-order reactions. So if it's a second order or other order or some more complicated thing yet, you won't get this nice relationship. What it says is two things at least, many things actually, but two main things. One is that the half-life is almost the same information as the rate constant itself. If I know the half-life somehow, if I measure it, I can get the rate constant by just multiplying by 0.693 and dividing by, well, let me write it, k is equal to 0.693 over t1/2, right? It works in reverse too. So if I take 0.693 and divide it by the half-life, then I get the rate constant. So you can get the rate constant automatically if you can measure the half-life. And the half-life is easy to measure, right? Because all you got to do is time how long it takes to lose half your stuff, and you got the half-life. So that's nice. The other thing is that this half-life doesn't depend on the initial concentration, doesn't depend on A0. And that means if we wait one half-life, that's what this plot is saying down here. If we wait one half-life, that's t1/2, well, who's to say that isn't the start of a new reaction, right? We can consider this new concentration to be our initial concentration again. And that means since the half-life doesn't depend on the initial concentration, if we wait another half-life, we should lose another half of our concentration. And if we wait another half-life after that, we should lose another half of our concentration, and so on. Every half-life, all the half-lives are the same, and that's only true for a first-order reaction. So this is another diagnostic test for a first-order reaction. Are the half-lives all the same? If I time how long it takes to lose half of my concentration, and then I wait and time how long it takes to lose half of that, and those two times are the same, or at least roughly the same, then I've got at least roughly first-order exponentially decaying behavior. So it's really easy to measure the half-life. You just wait a couple of half times. You just wait till you lose half your time, half your concentration. You wait again till you've lost half of that. And if both of those are the same, whatever that time was, that's your half-life, and that gives you the rate constant. You can do it almost by just counting. You almost don't even need a watch, if at least it isn't too fast of a reaction. And so let's do an example of doing that. Let's suppose caffeine in the bloodstream is the thing that we're worried about. So the problem says the concentration of caffeine in the bloodstream, that is, how long does your coffee last before you go into depression from caffeine, depression, is found to fall from 1 milligram per liter to 0.5 milligrams per liter in 7 hours, and then to 0.25 milligrams per liter in 14 hours. Question is the destruction for caffeine in your bloodstream a first-order process? And second, if it's first order, what's the rate constant for that process? Well, if you look, it fell by a factor of 2, so that's one half-life in 7 hours, and it fell by another factor of 2 in a total of 14 hours, which is another 7 hours. And so, is it first order? Yes, the two half-lives are the same, at least as far as we can tell from the data we've been given. What's the rate constant? Well, the half-life is 7 hours. The rate constant is therefore log 2, or 0.693 divided by 7 hours, and that's about 0.099 hours to the minus 1. You could change that to other units if you like, but a time to the minus 1, it's usually seconds to the minus 1, but hours to the minus 1 are a perfectly valid unit too. All first-order rate constants have units of time to the minus 1 in some time unit. Okay, that leads us to the first-order reaction. Let's see, do we want to go through the second-order reaction? No, let's hold off and do the second-order reaction in a separate video.